Hello everyone, welcome back to the lecture series on Foundations of Deep Learning, Concepts and Applications. In our previous lecture, we have discussed about the architecture of ResNet using residual network. In today's session, we will speak about transfer learning. We will discuss transfer learning. So the contents for today's lecture is what is transfer learning, how does transfer learning work, approaches to transfer learning, advantages of transfer learning and applications of transfer learning in computer vision. So we'll start with what exactly is transfer learning. Transfer learning is a machine learning technique where a model trained on one task is reused as the foundation for the second task. Why do we need transfer learning? There are cases in real world tasks like medical images, satellite data, where we don't have a large labeled data set. So whenever there is limited data set, transfer learning becomes very useful. It enhances the performance because the models are trained from scratch on small data, often overfit, which means when we have a model which is already trained in a bigger data set, we can use that one for some other task. Now, in case we have a small data set for a specific task, and if we want to use that data set only to train a model from scratch, then it becomes very limited and it can overfit. So, using transfer learning enhances performance, particularly for the tasks which are having small data set. Time and cost efficiency. Training deep neural network from scratch can days or weeks. If we use transfer learning, that time and cost efficiency reduces. Adaptability. A model trained in one domain like natural images can be adapted to another like medical x-rays. So, we can use a model which is already trained in natural images like which is trained in ImageNet dataset, that we can adapt it for other medical x-ray images as well. How does transfer learning work? Suppose we have task 1. What is the task 1? We will see. Suppose we have, like I will just take the example of classifying images into 1000 classes using the ImageNet dataset. So, this is classification task. Pre-training of model has been done using that ImageNet dataset, and I have a model which is trained on ImageNet dataset, and the weights and biases we got to know for the best performing model. ImageNet dataset I am taking for example, it can be other datasets also. Now, the model trained with large datasets for task 1. What is my task 1? It is classification of images. This model has already learned general features like edges, shapes or word embeddings. Okay. It is because it has already learned from the huge data set, it has already learned features like edges, shapes or word embeddings in case of NLP. Now, we will reuse the model's knowledge. How do we reuse that one? We can do it in two ways. Keep the initial layers which captures general low level features, okay, and these are called the frozen layers. So, whatever low level features my model have already learned, I am keeping them, I am reusing them, and we all know these initial layers of the neural network, they are actually they are the ones which help in capturing the low level features. And then modify the final layers which are task specific to suit your problem. That means your final layers will have the fully connected layers, then we have the activation function there. So, those things, suppose in case of ImageNet dataset we had 1000 classes. So, we have used the fully connected layers with softmax activation function for 1000 classes. So, the output layer is having 1000 nodes. Now, in case I have a classification task which requires only 5 classes or which has 5 classes. So, in that case my output layers needs to be changed for 5 classes of a classification problem, the output nodes, the fully connected layers that can be changed, and these are called as the trainable layers. Now, in this way we are using this knowledge that has already been there in the pre-trained model for the task 2. What is the task 2? Suppose I have some medical images which tells what is the degree of tumor in a brain. So, it can be advanced level, or it can be mid level, it can be in the beginning level. So, like this 3 classifications I am having. So, that is task 2. Okay. So, I am using the model that is trained in ImageNet dataset, which is having 1000 classes, and reusing that same model for another medical diagnosis work or task which is having only 3 classes. Now, frozen and trainable layers in transfer learning. In frozen layers, we will see what is the difference. In frozen layers, what happens? In trainable layers, what happens? In frozen layers, the layers whose parameters, that is the weights and biases, are not updated during training on the new data set. So, whatever we have done the training using the big data set, the ImageNet data set in this example which I am speaking about from the beginning. So, we will not update the weights and biases of those frozen layers in the training for the new data set. Whereas in trainable layers, these layers whose parameters are updated through backpropagation during training on the new data set. What is my new data set here? It is the medical images having various levels of tumor, okay, images of various levels of tumor. Preserve previously learned features like edges, textures, shapes in vision models or grammar in NLP models. We are speaking about NLP also here because transfer learning is very much used in NLP task as well. Okay. And in trainable layers, allow the model to adapt and specialize to the new task or domain. So, trainable layers are the layers where the model adapts and specializes to the new task or domain. So, here in this case, it is a medical domain in which the new task is given. And capture dataset specific patterns that pre-trained layers may not have learned. So, it is basically what is happening, we are taking a pre-trained model which is trained in generalized dataset, and then we are making it specialized using some specialized small dataset, and during the training of these trainable layers, it captures the dataset specific patterns that the pre-trained layers may not have learned because they have never seen the images of, or even if they have seen, it might not be of this this many, or in case of your general data set. Now, what are the various approaches to transfer learning? We will see that. One is feature extraction, in which we use the representations learned by the pre-trained network to extract meaningful features for new samples of a specific task. Okay. And freeze all layers of the pre-trained model, only train a new classifier like softmax or dense layer on top of it. And this is useful when the target task has a small data set or when computation resources are limited. So, what we are doing here in feature extraction is we are keeping all the inside layers, your convolution, pooling, activation, everything, those layers you are keeping frozen. That means you are not touching the weights and biases of the pre-trained model. What you are training here with your new data set is only the new classifier or the dense layer that you are which is there at the top of the inside layers of the neural network. And so, this is just an image to show you. So, in this case, if this is the input image, a generalized image this is. So, convolution, pooling layers, etc., they are the frozen layers, and you can train with your new data set for the fully connected layers, the classifiers and the output layer. So, this is feature extraction. So, these are your trainable layers in your feature extraction. Whereas, there is another approach which is called as fine tuning. So, in fine tuning, a pre-trained model's parameters are further trained or fine tuned on the target task's dataset along with the additional layers. So, what exactly here we do? We unfreeze some of the layers of the pre-trained or base model, retrain them on the new dataset with smaller learning rate, allow the model to adapt its knowledge to the new domain. And it is typically used when the target task dataset is relatively large and similar to the pre-trained model's dataset. So, here if you see, this is the normal convolution layers, convolution operations, in CNN architecture, and in case of fine tuning, what happens is we unfree some of the internal layers also of the pre-trained model, and we retrain them on the new data set. So, it is not only the top layers like the classifier or the fully connected layers, but inside convolution layers also we change number of filters, number of layers, those things we change, and this is done in cases where the target task data set is relatively large. If we do the same thing with a dataset tasks dataset which is very small, it will overfit. But if we have a relatively large dataset and similar to the pre-trained models dataset, in that case we can do the fine tuning. So, these are the trainable layers in case of fine tuning. Now, advantages of transfer learning: it reduces training time as it starts with pre-trained knowledge instead of training from scratch, requires less data and hence useful when the target task has limited label data, example in medicine, defense, etc. Pre-trained features usually generalizes well, giving better accuracy compared to models trained from the scratch, thus improving performance and saves computational power and storage. So, these are the main advantages, and this transfer learning have lot of applications in computer vision as well as in NLP. Now, applications of transfer learning in computer vision we will see. In computer vision, we have the popular pre-trained models which are like VGG, which is Visual Geometry Groups model, VGG 16 and 19, ResNet models, ResNet 50, ResNet 101, Inception model, that the GoogleNet model, Inception V3, MobileNet models, then we have EfficientNet, DenseNet. These are the popular pre-trained models in computer vision. So, what do? We take them, yellow also, you only look once. This is another very standard CNN architecture which we will study in my subsequent lectures. And so, these are the pre-trained models which are very much used in computer vision. And for which type of applications do we use these pre-trained models? They are used in image classification, object detection and recognition, image segmentation, face recognition. So, these are the applications of transfer learning. We also have medical imaging. Okay. So, these are the places where we have application of transfer learning. Now, quickly we will see there are two small things which are few shot and zero shot learning. We will have a look into what are they and how they are related to transfer learning. So, few shot and zero shot learning are specific applications of transfer learning where the model transfers the knowledge from pre-training to new task with very limited or no labeled data. So, you can use a pre-trained model with a very limited data or no labeled data for a new task. So, we will see what is the difference between few shot learning and zero shot learning. In few shot learning, the model learns to perform a new task with only a few labeled examples per class. Okay. So, it is using the pre-trained model's knowledge and then you show the model few examples and then it will be able to perform the new task. So, this is called as few shot learning, whereas there is something called as the zero shot learning in which the model performs a task without seeing any labeled examples of that task during training. So, this is called as zero shot learning. These are also two applications of transfer learning. With this one, I come to the end of this session. So, a quick summary or quick revision of what we have gone through in this session. We have started our session with the introduction to transfer learning. What exactly it is? It is a way in which a model which is trained in a bigger data set from scratch, that model's weights and biases are used for performing a new task. So, that is what is transfer learning. Then we have seen why transfer learning is important. We have seen because training any model from the scratch is requires a lot of time. It requires a lot of data. So, wherever the tasks in the tasks where we have very limited amount of data, we don't start training a model from the scratch. We use these pre-trained models. Also, it reduces the computational cost because we are not training it from the scratch. We are using some portion of the pre-trained models, weights and biases, and we are just training one portion of the neural network. Now, we have seen what are the approaches of transfer learning, like fine tuning and feature extraction. What are they? And we have seen what are the frozen layers and what are the trainable layers, and how these frozen layers and trainable layers can be changed in feature extraction. And in case of fine tuning, we have seen in feature extraction, we always freeze the internal layers and only the output, the fully connected layers, the activation functions, those portions get trained for the new task. Whereas in fine tuning, we open up some portion of the dense layers also inside neural network, the deeper portions, and then we retrain it with a new data set. Okay, so this is fine tuning. And then we have seen what are the applications of transfer learning in computer vision. What are the pre-trained models that are used in computer vision applications? So pre-trained models, like whatever models we have learned till now, it's like VGG 16, 19, GoogleNet, then ResNet. So these are all the things that we use for as pre-trained models, and that helps in improving the accuracy as well as in a reduced time. And then we have gone through what is zero shot learning and few shot learning. It's also an application of transfer learning, where we in zero shot learning, no new examples are shown, only for the new task, and in few shot learning, few examples are shown to the or given to the for the new task, and using the entire pre-trained model's knowledge for the second task. So with this one, I conclude the transfer learning topic. In the next session, you will have a hands-on session on transfer learning, how to use transfer learning, and also there you will learn about how to use ensemble models in transfer learning. So with that one, I conclude today's session. Until I meet you for the next session, keep learning. Thank you.